Hi, my name is Jaleel Salhi,
And my name is Kuhn.
and we want to show you all what we've been working on this summer with Professor Honglak Lee at the University of Michigan.
We investigated the problem of detecting and tracking objects and video data. And at the end of the summer, we built our own system for this purpose.
Nice. You're probably unaware that object detection and recognition plays a large role in many systems around us. Military drones use it to locate and track targets, waypoints, and other objects of interest. This is just an example of a UAV system locating and tracking this truck.
It is also used to retrieve statistical data on traffic. This application shown in this video counts and classifies different cars that pass by on this street.
By providing an object detection and tracking system for intubations, doctors might have an easier job carrying out tasks and analyzing video data from previous procedures. It may also allow researchers to collect labeled data more easily. Not only that, but it also brings us one step closer to autonomous medical systems.
The project can really be broken down into two main steps, a detection stage and a tracking stage. But detecting objects and images is a very hard task. One very intuitive idea to detect differences between objects is to break these objects down into a set of unique subparts. This is the main idea behind Pedro Felsenswab's deformable part-based models, which we implemented for our system. Take, for example, the human face. The human face can be distinguished because it has certain parts that define the face, the nose, the eyes, and the mouth. If we are able to find an object in a scene that has these parts in some sort of consistent structure, we are more easily able to classify this object as a face and the rest of the image as background.
Felsenswab's detector learns both of these subparts and their relative structure during training, so that the model becomes very robust, even with variations of appearance. This video of Ramanan's pose estimation demonstrates the division of the human into parts and how each part has a relative location with the others. Felsenswab captures the same information in his models.
We implemented this same technique to detect 4 parts in the typical airway anatomy: the carina, the epiglottis, the trachea, and the vocal cords. Each model contains unique subparts learned during training that help make each model unique to that object.
Now, how can we extend Felsenswab's idea to detect objects in a video? We used a combination of Felsenswab's detection algorithm with what is known as a hidden Markov model. A hidden Markov model is a system that models how a process moves from one state to the next given certain observations or potential states. In our case, the goal was to determine which sequence of states, in this case, the states are the bounding boxes, best represents the object's appearance in a video. For this, we implemented Andrew Viterbi's Viterbi algorithm for most likely sequence of states in a hidden Markov model.
The Viterbi algorithm is designed to choose the most probable path, or the sequence of states in a hidden Markov model, via the computation of interstate probabilities. In the case of object detection, we compute the probability of each bounding box from the ground up, so each bounding box per frame is associated with the bounding box in the previous frame that gave it the highest probability. This score is based on the location of the previous bounding box, as well as the airway part both boxes correspond to. Once we reach the final frame, we choose the bounding box with the highest probability and trace back from there, choosing our final sequence of bounding boxes and outputting a video accordingly.
Without applying Viterbi's method and just picking the best detection for each frame, you can get results that tend to be jittery and jump around a lot, even if some of the detections don't make much sense.
When applying the Viterbi algorithm, you end up with something like this. As you can see, the transitions between boxes are a lot smoother, and the transition between labels is more coherent and fluid.
Thanks for watching our video.
If you want to get in contact with us for whatever reason, our contact information will be at the end.
Special thanks goes to Professor Honglak Lee and the SURE staff for all the hard work they put in to give us this experience.
Thanks again.